Let's now explore the solution of the power flow calculation problem. In this lecture, we focus on the Newton-Raphson method and its application to tackle the power flow equations that were studied in the previous block. We previously defined the power equations at each bus and the vector x that comprises the unknown voltage phases and magnitudes. The Newton-Raphson method is used to solve these nonlinear active and reactive power equations at each relevant node or bus. The method starts with an initial guess of voltage phases and magnitudes, and iteratively refines them by computing the power mismatches P and Q. That is the difference between the specified and calculated powers. These mismatches are related to numerical corrections structured in the vector x through the Jacobian matrix, which represents the sensitivity of power injections to voltage changes. By solving for the correction vector x and updating the voltage magnitudes and phases at each step, the method quickly converges to an accurate solution of the power flow profile. The system of nonlinear power equations is expressed compactly using matrices and vectors. The power mismatch vector, which represents the difference between the specified and calculated active and reactive powers at each node, is multiplied by the inverse of the Jacobian matrix to obtain the correction vector. This correction vector is then applied to update the voltage magnitudes and angles at the nodes. Iterating this process systematically allows the method to converge efficiently to the solution of the power flow problem. The Jacobian matrix is divided into 4 blocks, each representing the sensitivity of power injections to changes in bus voltages. The top left block, G11, shows how active power changes with voltage angles, while the top right block, G12, relates active power to voltage magnitudes. The bottom left block, G21, represents how reactive power depends on voltage angles, and the bottom right block, G22, shows the sensitivity of reactive power to voltage magnitudes. This block structure helps to systematically compute the voltage corrections needed to reduce power mismatches and achieve convergence. The iterative power flow calculation using the Newton-Raphson method typically follows 7 steps. First, the Y-bus matrix is built based on the predefined network data. Second, initial guesses for bus voltage magnitudes and angles are set. Third, bus power injections are calculated using these voltages, and the power mismatch vector is computed as the difference between specified and calculated powers. Fourth, a stop criterion is applied to stop, for instance by checking the worst element of the mismatch vector if it is below a pre-specified tolerance error. Fifth, the Jacobian matrix is formed to relate power mismatches to voltage corrections. Sixth, the correction vector is calculated. Finally, the voltages are updated and they are used in the next iteration. The process is repeated until the mismatches are within an acceptable tolerance, indicating convergence to the system's power flow solution. To sum up, in this video you have learned about the application of Newton-Raphson method to iteratively solve the power flow calculation problem.